Okay, so here's the link to the first podcast on Lewis acids and bases for this snow day, and following this is the second part of today's lesson, which will be to calculate the pH of three different solutions. So before we begin this, let's look at it qualitatively, and first of all, looking at the three different solutions, what they have in common, you can see that the first one is a straight acid solution, acidic solution of acetic acid, which is a weak acid. So we can't say that the pH of this solution is 0. It'll be something less than that, since acetic acid is a weak acid. Second solution we have is acetic acid, but I've dumped in to that same solution some sodium acetate. What effect will that have on the pH if I have dumped in some acetate ion? What effect will that have on the pH? And then finally, a solution which isn't an acetic acid solution at all, but a solution of sodium acetate. And in this case, what effect will that have on the pH? So think about that for a moment. What is the ion formed when sodium acetate dissolves in water that is going to affect the pH? Remember, we have to think about sodium ion. Is that going to dissolve in water and be an acidic or a basic ion, or is it a neutral ion? Second of all, what happens when the acetate ion dissolves in water? Of course, the sodium ion isn't going to react with water and produce sodium hydroxide and hydrogen ion. That's why sodium ions are neutral. But the acetate ion will interact with water, producing base. And so, of course, then this solution, the sodium acetate solution, will be a basic solution, because basic solutions are those that have more hydroxide ions than hydrogen ions in solution, formed because the acetate ion interacts with the water. We don't think of it as an acidic solution because it forms acetic acid. We think of it as a basic solution because it is the hydroxide ion that is formed, making the hydroxide ion concentration be greater than the hydrogen ion. So moving forward, I want you to try to consider the stopping, pausing, calculating the pH of these three solutions before moving forward and on the podcast and looking at the work that I've done and shown for you. So pause it now and then begin again in a moment. Okay, so how did you do on the first one? The pH of the 1.0 molar acetic acid. We did this in class, a similar solution to that, 2.37 pH. Yes, it's less acidic than HCl, 1.0 molar HCl, right? 1.0 molar HCl is going to have a pH, because HCl is a strong acid, it'll have a pH equal to what? Well, the hydrogen ion concentration is going to be 1.0 molar, and the pH of 1.0 molar, what is that? That's equal to 0, isn't it? That's exactly right. So less acidic is acetic acid. That makes sense. Acetic acid is about that concentration, maybe even more dilute than that, would be what's in vinegar. But we certainly wouldn't want to put a pH of 1.0 molar on our salad. Not a good idea. All right, so moving along to the next one, what is the pH of, we're going to do this one next, the sodium acetate solution. So going about, how do you calculate this? We've got to consider the K for this problem. And it's not Ka, as we talked about before, it's actually Kb. How do you calculate Kb? Remember, you've got to use the Ka times Kb equals Kw. So what is the Kb for this problem? Well, you calculate it. All right, set it up. Notice that you have the KB was 5.6 times 10 to the minus 10. You're going to go through the motions in much the same way. Again, notice that the concentration here, 1.0 molar, is much greater than the value of K. So yes, X can be neglected. But notice this time, the X is not the hydrogen ion, but the hydroxide ion. So the first thing that you'll be calculating is POH, not pH. So you've calculated the POH here, and then you can convert that into pH by subtracting it from 14. Remember, pH plus POH equals 14. Could you figure that out by looking at this equation? Think about that. What is POH? Well, isn't that the negative log of the OH? Try taking the negative log of both sides of this equation mathematically. You could pause it and do it if you wanted to. Could you convert from this equation right here up to the one above by taking the negative log of both sides? Bet you could do it. Pause and go on if you'd like. That would be a good exercise. Alrighty. So the final calculation is a situation in which you have a combination of two things in your beaker. For example, you have the weak acid, acetic acid, and you also have dumped in some sodium acetate. Now, instead of having 0 acetate ions, which is how we did the first problem, now you've started off with an equal amount of the acetate ion and the acetic acid. But since you have some acetic acid in solution, it's not a Kb problem, it's simply a Ka problem. But we've shifted the equilibrium because of the presence of the acid. Notice the setup is pretty similar again, but the process is a little bit more involved because now we have X being subtracted from the 1.0 but added to the 1.0 on this side. Did you calculate it? Pause now and see if you can go forward. Can you neglect this X? What happens? Well, voila! How nice is this? Look at this, how the mathematics, when X is neglected, when it's added to and subtracted from, the value of X is actually smaller. The percent dissociation decreases when you have this common ion of the acetate being added. It shifts the equilibrium backwards. Less acetic acid dissociates because of the presence of this acetate ion. And so the pH, the final pH, is even less acidic, higher pH. And look at the mathematics here. Wow, how nice is that? So to review, was your prediction using Le Chatelier's principle consistent with the values that we obtained here? More acidic with just pure acetic acid? Definitely basic with the salt of a weak acid. The sodium salt of acetic acid is the salt of a weak acid. It will be basic, yes. Sodium acetate is a basic salt. And then in the middle, shifting the equilibrium. Is this what you predicted? One final note, when we get into chapter 15, a buffer is defined as a combination of both a weak acid and its conjugate base. That is this example of the second solution here. And we'll study what happens with buffer solutions. If you think about having learned this concept in introductory courses, what does a buffer do? What does buffered aspirin do? Why do we take buffered aspirin? What effect is it supposed to have on our stomach? And think about it from a practical aspect before we move into this concept. But you've already here done a calculation here. All right, that concludes tonight's podcast. That's 2 of them. And enjoy the rest of your afternoon.